Okay, so hello everyone. I think we can start mostly with the introduction. So for this session, which will be the last of the Powersys user conference, I'm very glad to welcome two speakers, Michele Merelli from Enginsoft, Powersys partners, and for Particleworks software, and Didier Zefack from Powersys, so my colleague Didier. So I will introduce you to them very shortly. They will talk about thermal optimization of oil-cooled electric motor by using moving particle simulation. So Michele is a project engineer in Enginsoft Italy and pre-post sales manager for Particleworks Europe. His technical expertise spans e-motor cooling, consumer products, and non-Newtonian fluid modeling. Didier Zefack has more than 7 years of experience as JMAG simulation support engineer at Powersys Solutions. He supported many companies and universities on different simulation projects. He received 2 professional master's degrees, first in computational engineering for FEA simulation of phenomena governed by the fluid and solid mechanics, and secondly in mechatronics for synergistic integration of mechanical engineering, electronics, and intelligent computer control in design and manufacture of product and processes. In addition to JMAG, Didier also works on multi-physics CFD tool to provide a complete solution for electric motors design and optimization. So just before starting this presentation, I just want to remind you that you can ask questions during the presentation using the Q&A panel or the chat panel, either directly on the presentation screen or on the Wova platform. So we will keep some time at the end of the presentation to answer to all of your questions. So it will be a good opportunity for you to exchange with the speakers. So I think Didier, it's your turn to start.
It's
actually
Michele will
Oh,
start.
Michele, sorry.
Yeah.
Sorry.
Yeah, sorry.
So I will stop sharing my screen, and now you can, I think, start sharing yours.
Okay. So hello everyone, and thanks for joining this webinar. And thank you, Corentin, for your introduction, and to Powersys for the invite, the very kind invite. So as already Corentin was mentioning, today we will talk about the thermal optimization of oil-cooled e-motors. And we will especially talk about the coupling that we can have between Particleworks, so the CFD tools that allow us to understand the fluidodynamics of the system, and JMAG. So I will just list the agenda and the points of today's meeting. So first I will introduce the motivation and why we needed to study with digital modeling with simulation this kind of system, and why in the next years it will be more and more important to do so. Then we will see and we will talk about the CFD tools, Particleworks, and I will explain you what are the differences between this meshless approach to other more conventional software that you might be aware of. And then we will see the application of the software and also some validation that we already had, also in the field of electric motor. In a second stage, I will show you all the steps and the workflow that usually are done in Particleworks to simulate an electric motor. So I will give you an idea of all the steps and how they then integrate to JMAG in this case. And on the last part of my talk, I will also show you a little bit of Particleworks graphic user interface, so you can understand better also how the software looks and what are the features in terms of visualization and what is the software like, basically. Later, I will explain you what is the most important post-processing tool that we want to use for the coupling with JMAG. So the mapping of the HTC variable onto the specific elements that we want to analyze and integrate in the FEA analysis. And then Didier will take over and will explain how the solution from Particleworks was moved to JMAG and what results we were able to achieve with some conclusions. So the motivation are the following. Why do we need to study with a simulation model, electric motors? Well, ERV engineering showed that in the next decade, it will be increasingly important to augment the power density of electric motors. And in fact, we see from the graph that is expected an increase of a factor of 10 approximately. At the same time, we will need in the coming years to increase the torque output from this kind of machines, the drive efficiency, and also we will need to lower the costs. To tackle all of these problems, we for sure have to optimize the system, and especially it's clear when we consider the power density that will be required. It's clear that external or air cooling approaches won't be sufficient. More and more, we will see running wet e-motors and jet-cooled e-motors are increasingly important application for to deal with the cooling of this kind of systems. Usually, what we see, of course, traditionally, is this kind of workflow, moving from the CAD. What usually is done, and it's also nowadays done, is to, of course, prepare a physical prototype, study the working condition, evaluate the temperature inside the e-motor, and try to have a positive loop and iterative approach between the first prototype and the second and the third, and so on. What we propose, however, is that with Particleworks and with simulation tools, we can speed up significantly this iteration step, and we can lower the cost connected with the physical models, and we can have a feedback in just a few days, a feedback concerning a certain geometry, a certain working condition, a certain load. In this way, we can achieve only to construct only one physical prototype, and we can go straight to that working final prototype. This is the objective of the digital modeling and the simulation with Particleworks. So let's understand a little bit more about the software. Particleworks is a CFD tool that uses a meshless approach called moving particle simulation. So instead of having to generate a mesh, a computational mesh, like in other traditional CFD tools, the software discretized, you can see it at the beginning of the video, discretized the fluid domain in particles, and those particles become the computational nodes on which we solve the Navier-Stokes equation. We do this with a dynamic mesh because, of course, due to the splashing and the movement of the fluid, the computational nodes will move around in the system. So we solve the usual equation with a Lagrangian approach. Because of this, this software is very suitable to study free surface flows or liquid jets in general, splashing phenomena. Every time we see this kind of phenomena in the fluid domain, we know that we are dealing with something that Particleworks can tackle pretty efficiently. Particleworks enables different type of thermal analysis. We will see what are the approaches, and depending on the type of application and the complexity of the system, we can, of course, use one of them. So just to underline the differences also with another scheme, and this is the most important, of course, difference. Compared to conventional method where we have to discretize basically everywhere, domain, the fluid domain, and we have also to think in advance what, let's say, what phenomena we would expect and what resolution we should use in the most critical areas. As compared to this conventional method, MPS allows the generation of computational nodes only where needed, and we follow the computational nodes during the solution, shifting the interest to specific areas only where we need them. So, of course, this is ideal, again, if we want to study jets, splashing phenomena, and these kind of things. Let's have a look at the application. Because of the feature of the software and the fact that we don't have, for instance, to generate a mesh, historically, of the first application of the software were in the field of gearboxes and transmissions. Here we have a lot of rotating elements that are meshing together. And of course, when we have to construct a dynamic mesh of this system, it can be very demanding and time consuming. In Particleworks, we can directly go to the simulation. Other type of analysis are also possible, such as engine lubrication and also cooling, and also electric motors cooling. So this is increasingly important as, of course, it's also the topic of today's meeting. This is a very important application. We are working with many players in the field of developing the next generation of e-motors. Also, highly viscous or non-Newtonian fluids can be modeled in Particleworks, and so because of that, we can analyze some food-related, some food processing phenomena or glue, cement, this kind of materials as well. Other applications are bearings lubrication, either with a grease, so a very non-Newtonian fluid, or with some more traditional or conventional oil behaviors. We also have other applications in the field of hydroturbines, mixers, and also civil engineering. So really the fields we can analyze with Particleworks are different and various, and more and more every day we see, let's say, new aspect of R&D investigated with this kind of approach. Just to conclude on the introduction of Particleworks, I want to strengthen this concept. As I mentioned, before this kind of software were available, in some cases, some systems were not possible to simulate and to digitally analyze. Since the mesh generation steps are not present, and also since the fact that the algorithm behind Particleworks are easily parallelizable, and because of that, they can take advantage of some architecture, computational architecture, such as graphic cards, where a lot of cores are present and working in parallel. Because of these features, the simulation time of a simulation in Particleworks and with the moving particle simulation can take 1 or 2 days. So usually they are very much compatible with the R&D workflow that you see in industrial applications. So also the CAD preparation step before the mesh, it's not really needed. So we don't have to clean the geometry, we don't have to simplify the geometry. The workflow is very fast, and again, it's compatible with usual R&D workflows. The thermal analysis and possibilities in Particleworks are various. We can have, let's say, HTC, heat transfer coefficient estimation from nacelle correlation. So with a type of extraction of the HTC that is temperature independent, and it's only dependent on the fluid properties and the flow properties. So let's say the most basic and important approach is to extract this type of correlations. From this type of correlation, we extract the HTC, and we transfer from the CFD solution to the FEA thermal simulation the maps of this kind of HTC. So this is what is also presented in this meeting today. So we will see exactly this approach, where FEA thermal simulation is performed in JMAG. Other type of simulations or thermal analysis that can be done in Particleworks are also conjugated in heat transfer. So we can analyze, in theory, also inside Particleworks, and we will see this, the thermal exchange between the fluid and the solid, and we can take into account the variation of temperature both in the solid and the fluid. Outputting also the heat fluxes and these kind of things. So let's now have a look at some validation of the software. First, let's say for the first time type of application that were gearboxes, then we move towards some more closely related validation connected with the thermal analysis and the e-motor cooling. So as I mentioned at the beginning, this software was used and it's used to analyze gearboxes and the lubrication of this kind of system. The first validation that we had was with this physical prototype constructed with a collaboration with Comer Industries, a company based in Italy that, let's say, designed these kind of transmissions. And as you can see, on the right side, we have the traditional approach. We have a clear case in which we want to expect the lubrication of the bearings in particular. So the objective here was to compare the lubrication of the three set of bearings between the experimental setup and the digital model. So what they did was basically to set 4 degrees of lubrication, and the test was to understand how well the two systems correlated based on this scale. So already from the video, you can see that there are very good correlations between the system. In fact, we can see that oil can reach easily the middle bearings, while on the top we see that clearly there is a lack of oil on this side. This type of consideration and analysis was done for different type of load cases and also mounting positions. And as you can see, there was a very good agreement of the lubrication level predicted by Particleworks as compared to the clear case analyzed experimentally. Another type of validation that we had at the beginning was this thermal analysis performed with Wärtsilä. In this piston, we basically monitored, and together with Wärtsilä, we monitored the temperature distribution measured by these thermocouples placed inside the piston, and we wanted to understand how the temperature distribution could correlate with the simulation from Particleworks. Here you see a graph showing the temperature for different thermocouples. In red, you see the prediction from Particleworks, and in blue, the measured values. As you can see, the trend is very well captured, and there is a good agreement between the two. In the same test, we evaluated how the correlation between the simulated and the measured temperature could resist for different loads. And as you can see, it's not just for the 100% load that we can capture and we can have a correlation between the simulated and the measured temperature, but also for different loads, we saw similar behaviors of the digital model. Moving now to a more, let's say, a more recent validation that is in the field of e-motors, so very much connected with what we want to discuss today and we will see today. Here I report some preliminary results that are already available at the link that you can get from the QR code here. This presentation is connected with a collaboration that we had with Ricardo, and Ricardo will present these results in detail during the next CHI conference. It's gonna be at the end of November, and this CHI conference is organized by Enginsoft in Italy annually. It's very similar to the Powersys conference, and also for us this year will be online. So if you are interested, you can check on that. So as I mentioned, we work strongly with a lot of R&D and companies, a lot of R&D centers in companies, and the results I will talk about are reported from a collaboration with Ricardo. The target was to monitor and understand how well, again, the digital model could predict the temperature distribution inside the windings of an e-motor analyzed by Ricardo experimentally. Of course, you are well aware, I think, that small variation in temperature in the windings region can cause important losses and important inefficiencies, and also the maintenance connected with this small variation of temperature can be can cost a lot of working lifetime. So the focus is to really understand and optimize the cooling in these kind of areas. Let's understand how we can analyze that together with other aspects using Particleworks, and let's understand what is the workflow and what are the observables that we can get from the CFD simulation. So first, of course, we want to model the e-motor and the CFD of that. So what we can do is to, for instance, analyze the flow distribution inside the rotor or other injecting channel, depending on the load case, and we can understand how the flow splits and distributes over all the channels. We can include both implicitly or explicitly an interaction with air. So in fact, of course, windage effects are also very important in this kind of system. Air does have an important role in moving oil around, and in Particleworks we can either have a one-way coupling between an air field that is pre-calculated either with another software or with Particleworks itself, or we can also simulate in a multi-phase simulation the two phases, and we can have a two-way coupling between air and oil. And at the end, of course, the most important observable will be the oil distribution in the inside the e-motor, and possible accumulation zones, and of course the heat transfer coefficient. So once we get a stable system, we want to map using the mapping post-processing tool that I will explain. So we want to map the HTC onto all the parts that we are interested to model at a later stage with an FEA analysis. So we get this kind of map and we transfer the maps either to an external FEA solver, for instance, again, JMAG, in order to include all the joule losses and the thermal heating of the elements. But what we can also do, just to mention, is to analyze the variation of temperature in the solid or in the windings state or any other element you are interested in inside Particleworks. So it's a new feature of the software. Of course, doesn't have the same flexibility that other FEA analysis tool offer. So the discretization of the windings is there is not a lot of control on some aspects, some boundary conditions, some discretization of the windings, but I just want to mention that it's also possible to have in the same simulation all the type of analysis together. So let's have a look now at the results in the temperature distribution. So as I mentioned, the windings were the most important elements that were monitored in this confirmation test. To correctly model for the material properties of the windings, we also took into account the potting material surrounding the windings. So we corrected the HTC with the formulas, the correct formulas to, of course, include also this effect. And the temperature was compared in 6 different locations that were the 6 locations where Ricardo had data point on. So the objective and the target was to achieve a maximum difference between the predicted and the measured temperature of 5 degrees Celsius. This was actually found to be true for all the 6 points. In fact, we saw a variation between the 2 temperature of only basically half of that. So the maximum variation that we had and delta was 2.8 degrees Celsius. And as you can see, we are for other points well below 2. So, of course, analyzing the temperature distribution of critical areas is one of the most important aspects that we can analyze with this type of approach. But there are other observable, I mentioned already, that we can extract from Particleworks. We have the possibility to optimize the flow distribution inside the rotor. We have the possibility to optimize the jet direction and the jet direction, basically impinging on the different areas. We can also have a look at the air gap and we can understand if there is any pollution of oil inside the air gap. You see here a map showing in light blue where oil gets trapped inside the air gap. And of course, minimizing this effect is important to increase the, let's say, the working life of this kind of system and also to reduce the churning losses. Okay, let's now just have a quick look at Particleworks and how the graphic user interface looks and what type of observable we can have. So this is the basic window that you will find in a Particleworks project. You have a scene showing your simulation with all the geometrical elements and also the results. On top here, you have the basic buttons to create a new project, to save, to do some pre or post-processing. So actually all the post-processing is gathered on top here. So as you can see, both the pre-process and the post-process and also the visualization of the results are on the same window, on the same software, on the same graphic user interface. And this is very convenient because during the simulation already, you can visualize the results. You can do some post-processing without having to close or open new graphic user interface. On the left here, we have the outline of a certain scene. Every scene is basically a simulation in Particleworks. And the outline of the scene collects all the inputs, geometrical elements, such as the bearings that I'm showing or not, or the casing. And then in this case, we had 6 inflows that I'm highlighting on top there, and other geometrical elements that you usually find in this kind of system. At the bottom here, we have also the results, so we can see the particles that are generated, and other in the outline we see other, let's say, visualization or post-processing results. As you can see at the bottom, we have a player. We can play our simulation and have a look at the results. And also using the view tool called Snapshot, we can very quickly move to a visualization that we liked, such as this one, in which we have also reported the first mapping that we did. Okay, so we did a mapping of the HTC, and with the snapshot functionality that is in Particleworks, we can easily get that view with that result. And as you can see now, I move back to the old visualization with the particles and without the mapping by applying the other snapshot. Very convenient. So as I mentioned, this is the type of map and the type of post-processing that we want to have to then transfer the CSV file to JMAG. So to do that, we click on top here, the mapping post-processing tool. A window opens on the right. We just average over a certain amount of frames. We select the geometry we want to map onto, and we enable the CSV output, of course. And once we run this, we basically get the mapping that you see. And also, if we open the directory, we also see the CSV mapping that, as Didier in a few seconds will explain, can be imported as a boundary condition, HTC boundary condition, to JMAG. So I think I'm done for my presentation, my part of the presentation. I will leave the floor to Didier for the JMAG part. Thank you for.
Thank you. Okay, so let me share my screen and let me know if you can see my screen.
Yes, we can see your screen.
Okay, okay. So thank you. So now I will start with the JMAG part in order to show you how we can use the HTC map data that we can get from Particleworks. So before starting the demonstration, I want to give you some information about JMAG. So note that JMAG, it is an advanced finite element simulation tool that allow you to design any type of electrical motor. So this tool was created since '83 by Digital Corporation. So it is a Japan company based in Tokyo. So JMAG, it is an advanced tool that allow you to develop or to design any type of electrical motors for electrical car or electric hybrid car. Or you can also use JMAG to develop any type of power transformer. So regarding the analysis that we can do with JMAG, so we have 5 types of analysis that you can implement into JMAG, but I will not go in detail. What I want to say here is that we can use the multi field to calculate the losses and then use these losses into the thermal analysis to get the temperature. So the advantage of JMAG is that you will be able to make some coupling analysis between these different analysis. So what I will show, what I will use in the demo is the coupling between the multi field and the thermal. So if you look in from the market, you will see that any type of electrical motor that you will find from the automotive to aerospace market can be simulated into JMAG. So if you look again, the different step to design the motor. So we start from basic design to the validation. So at each step of the design, JMAG will provide you a specific tool. So for example, for the basic design, you can use the JMAG Express tool. So JMAG Express, it is a 2D motor tool which contain a different type of motor card. So with this tool, you will be able to get in 1 second all the basic characteristics of your motor. Then you can switch to the detail analysis by using JMAG Designer. So today I want to focus only on the coupling analysis, on the coupling between JMAG Designer and some external software like Particleworks. So I want to show you how the post-processing can be done into JMAG using some result calculated by other software. And for the validation, you can also use JMAG Active to convert your 2D or 3D finite element in order to get a 1D component that you can import into your CQ software or your motor test bench for some testing or validation. Okay, so before starting the demonstration, so it is very important. So when you make some detail analysis of e-motor, so it is very important to know how the loss is produced and how this can be converted into the temperature. So this is why into JMAG you will be able to calculate some losses. So for example, the first losses is the iron losses. So JMAG is able to calculate the iron losses due to the variation of the multiflux inside the magnetic part like rotor or stator. And then JMAG can also calculate the wire losses, so the loss produced from the winding, and also the loss produced from the other conductor that you have inside the motors. So here, this is the general step to link Particleworks with JMAG. So Michele show you the step to run some fluid flow into Particleworks, then how to export the HTC data. So this file need to be prepared. So some data. So when you export the mapping, you will get some CSV file with a lot of information. So you need to use some particular tool in order to remove the data that is not necessary for the coupling. Okay, then when you have this file, here this is the process that I done in order to import this HCC data into JMAG thermal analysis for temperature analysis. So let me show you some example of models. Okay. So this is the models. Here, this is the full models. Here. Okay, so the first thing is to create the losses. So the magnetic analysis in order to calculate the losses. So this is why Here you have the project manager of JMAG, which will contain all the 3D, 2D model with all the study. Here you have some button, and in your right you have the toolbox, which contain the material database for different part of your motors. You also have some condition that you can apply to your study in order to make some specific calculation. So here I can show you, for example, into the magnetic analysis. So here I can show you the list of the analysis that you can apply to this 3D model. So the first thing, I use the 3D magnetic analysis for the loss calculation. Then here you can see the list of the material that I apply to each part of my motors. Here, this is a different condition that I apply, for example, condition to calculate the losses from the stator and the rotor. So this is the condition to define the winding configuration, and this is the condition to extract the heat sources, so the heat loss of each coil. So this condition is very important when you want to link the magnetic calculation with the thermal. Yeah. So here I can show you the meshing. I can also show you the circuit of the model. So this is the input current and the three-phase winding of the motors. Then I can also show you the joule losses from the winding. The joule loss from the rotor side, because so it is induction motor, where inside the rotor we have the squared cage. So this is the joule loss for the squared cage bar from the rotors, and this is the iron losses. So this is the iron loss for the rotors, and also here a bit for the stator. Okay, so when you have these losses, then I can switch to the thermal analysis. So here for the thermal analysis, you need to define into the material property. So you need to define the thermal property of the material, for example, the thermal conductivity, and also the specific heat of each solid. Then you need also to define some condition. So for example, here you need to define some heat transfer condition. Note that into JMAG, we will not model the fluid. So JMAG, the thermal analysis into JMAG is the thermal analysis for the solid. So it's only for the solid, not for the fluid. So this is why if some phase of the solid are in contact with the fluid, so you can model, you can use the heat transfer condition to model the contact between the solid and the fluid. So here, for example, you will be able to define, for example, the reference temperature and, for example, the heat condition. So here, when you have the heat data that we have calculated from Particleworks, so the heat data was calculated on the surface between the coil and the oil. So this is why I will use the heat transfer boundary condition, then select all the faces which are the faces of the coil which are in contact with the oil. Then I will apply it using this condition. So here I define the reference temperature. Then here I will specify the link to this HTC data here. Yeah. And here you can also tell how you want to read the CSFI. So if you want to start from the first line or from the line 2, so you can define it here. So after that, you can also define some contact between some faces if you want to take into account some thermal, some recent thermal property or some heat, some insulation effect. So you can use thermal contact thermal condition. So here I can show you the meshing, and I can also sorry. So this is the mesh. Maybe I can hide the cases. So this is the meshing. Then now I can show you the HTC first. I need to remove this one. Okay, I need to remove some shell mesh so that we can just have okay. So this is the HTC distribution that Michele show you from Particleworks. Yeah. Yeah. So then I can show you the temperature. With temperature of internal. So here you can see the distribution of the temperature around the coil and also inside the rotor part. Yeah. So yeah. So with Michele, we have done a lot of example. So this is one with the rotative motor. So we have also done some example with the transformer. So maybe I can show you the result that we got with the temperature distribution. So I also make the same process to calculate all the losses. So this is the inside of the transformer. Maybe I can show you all the losses. So this is the iron loss from the copper of the transformer. This is also the joule loss from the other conductor of the transformer and the wire. Then here I made the thermal analysis. So here you can confirm the temperature distribution. But here you can see I define some heat transfer, condition to define the contact between some solid with the oil. So for example, here is that I have import the HTC map calculate from Particleworks. So for all the solid which are in contact with the oil, I define the HTC data. So I can also show you the HTC distribution. Okay, so here you can see the HTC distribution that we have from from JMAG. Okay. So in conclusion, so we have showed that Particleworks it is advanced meshless CFD software that it can help you to make some design of for your project in few weeks. So we also show you the workflow of Particleworks for e-motor design. We have shown you that several benchmark was done with Particleworks, such as the benchmark with Ricardo. So this benchmark which was done in order to validate the temperature distribution, and we have obtained, we have confirmed that the error was less than 2.8 degrees. So I also show you how to couple JMAG with Particleworks. So today we can do it manually, but we are still working in order to see how we can automatize this process. So if you, sorry, here you can also find from a JMAG website some demonstration tutorial. From YouTube, you can also check some demo of JMAG. So thank you for your attention. And if you have some questions, so feel free to ask us. Thank you.
Thank you, Didier. Thank you, Michele, for your presentation.
Thank you.
So we can now switch to the Q&A session. We don't have any questions so far. Oh, yes, I think we got a question about CFD. So I guess it's a question.
Yeah, we use CUDA.
Michele, are you using
I think.
CUDA or OpenCL?
I think we are using CUDA. I'm not 100% sure of what OpenCL is at the moment, but we use CUDA. Yeah, we are using CUDA.
Yeah.
And another question, would you capture heating effects from fast-moving, rotating surfaces?
Heating effect.
So right now, I don't think that feature is integrated. So let's say the solid-solid interface or solid-solid interaction won't cause any heating or no, not in that regard. We can have a fluid heating in closed gaps, for instance. We can model that, but not, let's say, friction effects, if that's the question. Yeah.
Okay, thank you, Michele. And solid to fluid?
Again, we can have a transfer between the two. We can have heating of fluid because of shear. So we can have shear heating effects that are important, also, especially with very viscous fluids. But yeah, the heating due to the friction. Okay, yeah, okay.
Okay, thank you, Michele. Any other question for Michele and Didier? You can wait a couple of seconds.
I think you have some.
New question. Would it be possible to calculate something like a thermal resistance for a ball bearing?
Yes, I think it's possible. Normally, this sometimes this thermal resistance is given by the manufacturer of the ball bearing. But I know that there is some formula to also get some approximation of thermal resistance of the ball bearing.
Okay, thank you, Didier.
Yeah.
Any other question? Yes. How inefficient is this method for simpler closed cooling channels without splashing?
Of course, like you lose a lot of the advantages that you can have for other type of phenomena, and also Particleworks deals with, let's say, incompressible fluids. That's also another, let's say, limitation of the software. But so I don't have a clear, let's say, scaling efficiency or inefficiency in this regard. It's just that, of course, it's much less favorable if you just analyze closed channel, and if that's the only objective of maybe not even rotating or not in some particular condition that favor Particleworks over other software in the entire workflow, not just the simulation part.
Okay, thank you.
Yeah.
Okay, so I think we are done for the question. So I would like to thank you again, Didier and Michele, for your presentation. And
You're
I
welcome.
would like also to thank all the attendees. So it was the last presentation of the Powersys user conference, a closing session. So I hope you really enjoyed this 2 weeks event we organized online for the first time. So let us know if you have any feedback about it. Of course, it's always interesting to see what we can improve. And I wish you a nice rest of your day and a very, very good weekend.
Thank you so much.
Bye bye.
Thank you.
Thank you all.
Okay. Thank you. Right. Yeah. Thank you.